welcome to the 2020 Wyong Field Days. It's my
2020?
pleasure.
2020?
2020, it's
You
happened.
said 21.
Yeah, not quite. To welcome Dr. Brian Clarke, who's familiar to most of you, I should imagine, talking on matching power from devices to loads and with high power, the attendant problems. Thank you very much, Brian.
Thanks, Ryan. Okay, look, okay, now I'm not going to go over the stuff that Rakesh has covered. I'm going to very briefly sort of refer to propagation and those sorts of ionospheric conditions, but not in great detail. I'm going to be much more concerned with what happens here on Earth between you, your soldering iron, and your bits of metal out there. I hope all of my slides are readable. So, in general, I'm going to assume that you are English reading people and that you can read at something like 120 words per minute. Sorry? As good as my CW. Yes, that's right. So, some of these slides have quite a bit of material on them, but most of them are just coat hangers, and so I'm going to use the coat hangers to address various kinds of comments. I'm not going to read from my slides. I'm going to assume that you do that work. Have we got it going? Oops, too far. Let's go back one. Right, okay. So I'm going to be focusing on the physics and the electronics. I'm not going to be talking about solar wind or coronal mass ejections. Well, not very much anyway. I'm not going to assume a high level of technical knowledge. And on a previous presentation of this material, I did assume a very high level, and I suspect that I lost most of the audience. But they came back and asked me to do it again, so I've dropped down a little bit. Okay, so these are the things that you should be able to do at the end of my little chat. Now, there are some 30-odd slides here. About half a dozen of them are related to actual building of an antenna coupling unit. If we get invaded by the voice from down below, or we're told that there's some other kind of interruption, I may well skip that. But if you have your USB sticks or that kind of things, you can copy it off this machine here, or I've got a copy of the stick myself. If you've got your own computer, we can copy the material onto that. So there's no real handouts. Okay, let's look at the total system. Oh, in case you're wondering, this little symbol here is the radio club that I have belonged to for about 30 years. And so I usually produce these things, try them out there, and then... Okay, so let's look here. I'm going to put a series of boxes up here, and you're going to tell me what I'm going to put in them. Let's see, we've got a... One, two, three, four. Okay. Okay, so... Okay, so these are the various bits that you will use in your radio system, and let's assume they're connected up. So which one is going to be the power supply? Any guesses? You want bottom left? All right, I think that's a good idea. And the amplifier, the RF amplifier? This one? Okay. Okay, now where am I going to put the low pass filter? Same thing, power amplifier. Really? Maybe this is something we have some learnings. Okay, so where are we putting the low-pass filter? You want the low-pass filter here? All right. And where are we going to put the antenna coupling in? I guess the last box. Now you notice I don't call it an antenna tuning unit. Do you know what an antenna tuning is? It's a pair of side cutters. That's the only way you can tune an antenna, and if you've gone too far, it's brazing, welding and soldering to add the bit on that you shouldn't have cut off. That's the only way you can tune an antenna. So this thing is a coupler. I know it goes against the grain for Yaesu and Kenwood and Icom. They'll all tell you that they can sell you an antenna tuning unit, but they don't sell you the side cutters. All right, so that's the order of the bits. I think I might have pushed a button inadvertently. Let's see. Where are we? Oh no, we've got that. Okay, so we've got all the bits. Recognise this now. One other little thing. Where am I going to connect the ground system? Really? You're really sure about that? I know of at least 3 different kinds of ground systems. There's lightning ground, there's mains protection ground, and there's RF ground. So where are we going to connect the RF ground? Sorry? No. That's where your RF ground goes. All right? If you want mains protection, it goes here. And if you want lightning protection, it goes in here. So different kinds of grounding systems for different kinds of functions. And you use different kind of wire for each one of them as well. Okay. Let's move on a bit now. All right. So I'll be cunning. Let's say, let's assume that that's the surface of the Earth and we've got all this grass growing on it. Okay. Oh dear. Yeah, you're right. Okay. So sorry about that. I'll put it down. Okay. All right. We'll put him down. Thank you. Thank you for reminding me about that. Okay, and here we're going to put up our tower. We're going to have an antenna, and let's assume that it's going to be a moderately long antenna. And this is the length of our antenna. Okay, and we're going to send the signal off and try a different colour. Yep, that'll do. Way up here. We have the ionosphere, and that's somewhere between 90 and 900 kilometres. Okay, now the Earth down here has a radius r of about 6,400 kilometres. We have an antenna here which has a height h. And so you all know the distance to the horizon, don't you? That's why I've got the height of the antenna. So, if you want the distance, it's approximately equal to the square root of 2RH. Now I can give you the whole mathematics. So that's line of sight to the horizon. But a lot of the stuff that we do at HF, we're going to want to bounce off the ionosphere, and once it gets up to the ionosphere, we want it to bounce off the ground. So when we have a signal coming out of our antenna here, it's going to hit the ground, and it's going to go off into space. And if this distance here equals our wavelength, what are we going to get? of these two waves going out towards the ionosphere. We're going to get reinforcement. Now, if this is lambda upon 2, then we start getting cancellation. All right? So the idea that you put your antenna as high as possible may not be the best solution. Okay. And if you want to have a multiband antenna, then the actual length here is going to vary. Now, here's your takeoff angle here. It's the same as the takeoff angle out here. And you can calculate by trigonometry what that takeoff angle is going to be. And therefore, you can work out, if you really want to do the maths, what your range is. And I'm going to put on some slides very shortly to show you how you can get the range. So I'm going to assume a half-wave length of antenna, so resonant in free space. And it's absolutely clean, got no corrosion, no paint, no radome, so it's not inside the front of a bomber. It's not up on one of these towers where they've got a radome over the front to prevent birds eating the antenna. Okay, so when the takeoff angle here is less than 15 degrees, you can assume you're going to get pretty well lossless bounces off the ionosphere. But when it's above 15 degrees, you're going to get 20 dB each time the signal comes down from the ionosphere and hits the ground again. Now, I did put in here for more detailed ionosphere to see Roger, but I would suggest after Rakesh's presentation, maybe you should shift your affections to Rakesh. He'll give you a great deal of detail. But Roger's pretty good as well. So don't let me be seen to be putting Roger down. Rather, having heard Rakesh's, I would say, yes, that's pretty good stuff. Reminds me of when I was doing my engineering degree. Okay. Now, we assume that the dielectric coefficient of the air is static and that it's very close to that of a vacuum. It's not quite. And the ABC made a big mistake when it started putting satellites up in the sky and using signals between 30 and 60 gigs for bouncing signals out into the outback. And then when you have rain coming over, good night, RF. Now, what's the antenna height? I've shown the antenna height here above the grass, but in fact, most of the grass around here is sitting on some soil and sitting on some clay and then sitting on some sandstone. And soil, clay and sandstone have a very low likelihood of ionisation. So they're not a very good ground plane. You've actually got to, your actual real height of the antenna is somewhere down here. Now, if you want to know exactly the height of your antenna, you lay out a ground plane. Now, a quick way of getting ground plane is to go to one of the concrete places and buy a slab of Rio mesh and then just weld bits of wire on and bring that back to your transmitter. The other way is what the military do, is run out counterpoises. And so that gives you an exact height above ground. Bear in mind, though, that if your counterpoise is half wavelengths long, what's the voltage at the far end of the counterpoise? Yes, tempo de kill de cat. Now, the other thing that happens with our soil is that the chemistry changes over time, partly as a result of the weather. So we get erosion, part of the soil washes away, and so the composition of the soil changes. And the other major variant is mammon, i.e. building developers. And they'll lay concrete all over the place, which is a bloody good insulator, sometimes. And so you don't know what kind of ground you've got. Okay, what I've done is a series of calculations here using LNEC, which is one of the numerical equivalence calculation programs. And I've made certain kinds of assumptions, such as the antenna is very thin compared with the wavelength. Once the antenna gets to be a sizable fraction of the wavelength, then you start getting other kinds of effects, and the assumptions built into LNEC you have to start changing. But as you can see, we have here at one wavelength, 74 plus J08. So it's not quite resonant. It's very close to it. And as we come down in height, in other words, we've got building regulations that say you can't have an antenna more than 10 metres above ground and all that kind of stuff. Of course, there's ways around that. You use a hydraulic or an air-operated antenna that goes up at night, and the neighbours can't see it. And the radio inspector can't see it. And the local government and council inspector can't see it because it's at night time and they stop at 5 o'clock. Okay, here I'm coming down to shorter and shorter wavelengths. All of these slides are actually available on the USB stick if you want to go up there and copy. But if you want to take photographs, fine. You might want to go into the middle to do that. Okay, the first time we get a resonant antenna is at half a wavelength above ground. No J component. Now why, oh why, do we design our antennas and our transceivers and all that kind of things for 50 ohms? Why do we buy all this expensive RG213 50 ohm, allegedly, cable? Do you know why? Why?
Because a lot of people don't use dipoles, they're using inverted V's and the impedance starts to come down. So
if the impedance comes down, will you get to 70 or 50 ohms? All right, let's give you a little bit. If you use a ground plane antenna, in other words, a quarter wave, vertical, and your counterpoise around, what's the impedance of that antenna? 32 ohms, thereabouts, all right? And if you have a dipole out in space or sufficiently high above the ground that the ground effects are zero, the impedance is about 72 ohms. Now, when the American military wanted to kit out all of their people with good radio communications, they decided for logistics purposes they would have one cable, and it was the square root of 72 times 32, which is very near 50 ohms. And so because of the American military, all of our bloody transceivers and cables and antennas are designed for 50 ohms, which is not the best impedance. So think about it. RG8, RG52, all those 75 ohm cables may not be so bad after all. Anyway, later on I've used 50 ohms just for illustration purposes. And here we're getting right down very close to the ground until you've got an antenna that's virtually sitting on the ground, or as some people do when they're farmers, they might use the fence. There are problems with the fence, as we'll come to shortly, but very good for near vertical incidents. And of course the military love NVIS as well, because if they put up a vertical antenna, they get a radiation pattern that can lead to the enemy offering you a chance to join heaven, because they can RFID ID you. Simple. Whereas if you use NVIS, you can just talk to the troops. Now, when you're on your motor car, this is probably about what your antenna's like, if you're using HF on a motor vehicle. And look at the amount of J correction, quite a bit. So side cutters will not fix up the J component. Won't work. All right. We know now why the takeoff angle changes. It's to do with the frequency that you're using and hence the effective height of the antenna above ground. The height of the ionosphere, the D, E and F layers are at different heights, and so they will affect how far away your signal goes. So in those tables that we had back here, you see I've got two lots of range. I've got the daytime range and the nighttime range to allow for the difference between the D and the E and F layers. And what does the plus J mean? All of those antenna impedances were X plus J something or other. What's plus J mean? It's which?
Inductive.
You think so? They were capacitive because they're short. It's when an antenna is long, L, inductive. It would have been minus J. So plus J is when the current leads the voltage. If you charge up a capacitor, the current leads the voltage. Okay, we've covered the day change, or the change between day and night. Now, here we have another problem. You've put up this wonderful antenna, you've gone to Bunnings or your local teak electronic suppliers and so on, and you bought some lovely ground wire, or you bought some hard-drawn copper, and you string it up and you cut it to the right length, and maybe you even use an antenna analyzer and you get the correct length of the cable. And you leave it up there for a while. And the cockatoos come along and they'll adjust the length for you. And the cable, you might have put little joints in it where you connect up filters along the line. You might have a trapped antenna. So where you connect the piece of wire to the trap and then to the piece of wire going out the other end, there'll be some kind of intermetallic corrosion occurs, which will change the effective length of your antenna. Say you decide you're going to get around those problems by using insulated wire, and you put a coating over the wire. You buy, say, the old blue, the neutral wire, which has got the insulation on the outside, and so you think that the weather is not going to get in there and cause corrosion to the wire, and it probably won't. Well, not for 20 or 30 years until the PVC is melted. But the more you do that kind of thing, the resonant frequency falls as SWR. So let's just have a look at the effect. Here is a totally clean antenna for 70 centimetres. And you can see that here we go, SWR 1.038, and resonant frequency about 4.3 something or other, all right? Now, if we put a small coating of insulation on the outside of that piece of antenna wire, here's what happens. Okay, SWR comes to a lower frequency, the resonant frequency is lowered as well. Now, how many of you have antenna coupling units that can handle inductive and capacitance effects at 70 centimetres? How many? One? Nobody. Right. So what do? You have to fiddle around with little bits of capacitance to try and adjust for it. But this is just a warning about if you decide to string up some wire that you've picked up off the dump that's insulated and you think, it'll last forever. And this is what it'll do. So you can't rely on just measuring the wire. You actually have to check the resonance once it's up in place. All right, now we come to the important thing. I've been sort of hinting at VSWR. Now, I use VSWR because almost all of the instruments that you can afford measure voltage. You buy yourself a Yaesu or a J-Wacom or whatever kind of radio it is, and the meter is actually measuring voltage. If you've got a deep enough pocket, and you were back a few hundred years, you could have bought a Collins KWM2A, and the meter on there and the circuitry behind it was designed by Walter Brunn, and it was actually a power meter. But most of us just have voltmeters. And we make an assumption about the impedance of the line on which we are measuring that voltage. So what does it mean when we say we've got a VSWR of 1 to 1? Is that the only answer? If you have a mismatch, then it'll be more than that. It'll be sort of 2, 3 or 4 to 1. So 1 to 1, we believe we've...
The highest voltage, the lowest voltage.
That's what it is, yes. And I'll show you a couple of slides on that. What's the meaning of 1 to 1? Now, how else can you get no reflection? You can connect up a dummy load. That's right. Yes. The other thing you can do is you can use an infinite length of transmission line. And if you look at your mathematics, the impedance of the cable is, okay for infinite length. Now, okay, 20 or 30 wavelengths, it will be very close to that impedance. So if you get 1-to-1, may not be the best that you want. Now, next question is, where should you measure the VSWR? We had the boxes up here showing where the SWR meter was. Go.
At the antenna.
At the antenna. Why do you say that?
Well, then you remove the loss in the transmission line.
Only the loss? You also remove some of the J component that your transmission line is going to put in there. Okay, so here we have the black wire, or the black thing there is the transmitted signal. All right? The purple one is being reflected back. And as you can see, right now it's in phase. All right? When it's in phase, that means that the load at the end was purely resistive. Anywhere else, and the difference in heights, and they'll be out of phase, and so there is a more complex requirement. Okay, now the antenna does not know the difference between the outgoing signal and the incoming signal. All it can do is measure the actual voltage at various points along the antenna. And so when we do an algebraic sum of what was on the previous slide, this is the kind of result we get, where we have Vmax, Vmin, and it looks to me like we've got an SWR there of about 2-to-1. Okay, so this is what you're going to be measuring with a voltage standing wave ratio meter, wherever you happen to be measuring it. Now, the cable that I've shown here has no losses. So if this were the transmitter here and the antenna down that end, we would expect that to go down a little bit. But let's have a look at what happens. Come on, wakey, wakey. Okay. So here's very close to a real live example, that we've got a piece of RG58 between our transmitter and our antenna. And I've got two positions there for the directional couplers, which are the things that pick off the voltage to feed to your SWR meter. All right, so 3 dB of loss, you might think, oh, that's not too bad, that's only half power. But think about it. At 146 megs, 15 meters of cable will give you 3 dB loss. And if you go to 70 centimeters, 443, 445 and so on, only 10 meters of cable will give you 3 dB loss. If you then go to 23 centimeters, it's only 4.3 meters of cable that gives you 3 dB loss. Okay, now let's start off with 100 watts going out of here. What reaches the antenna? Sorry? Correct, because we've got 3 dB loss, so we've got 50 watts here. Now let's assume that antenna is a Yagi-Uda, and it has an impedance of 6 ohms, a very typical impedance for a compound antenna. So we're going to get some of that signal reflected back because we've used a 50 ohm lead and we're putting a 6 ohm device on the end. Now I won't go through all the mathematics for you, but if you measure the SWR here, you're going to get about 7.9 to 1. Okay, so we're feeding back something like 30 watts coming back this way, and we're going to lose another 50% of that if we measure it here. So the incoming power from the line is 15 watts. And the SWR is now going to show 2.3. And so you have your SWR meter here just at your transmitter, and you think, 2.3, that's all right, I can live with that. But then we follow your advice, and we measure it here, and we get 7.9, and we say, start again. Yeah. So where you measure SWR is quite important. So if you're going to hang a dipole up in the air and you're going to have a balun in the centre, hang your directional coupler just under the balun and bring a wire down, or be very smart, feed the DC down through the RF lead and use capacitive DC isolation. You don't need to have another piece of cable. So, a couple of takeaways here. RG58, it's a very normal sort of cable. It's about 6 millimetres in diameter. We use it everywhere. We think it's wonderful. But look at the losses. And then think about where you're going to measure the SWR. Okay, how are we going? Oh yes, we could just about design an antenna coupler unit now, I think. Okay, now I published a whole series of articles in Amateur Radio in 2005. So if you've got your old antique copies, then go back and you'll dig it all out, and there's all the mathematics in there in great detail, but I'll just rush through it quickly. Should we assume that the wire that we're going to use follows Ohm's law? And which part of Ohm's law? Now, many of you will believe let's see. Let's take this one. This is probably the one that you all got in your license conditions. The EMF is the current times the resistance, and we think the resistance is constant, but is it? Let's take R at our present value of temperature, and we're going to get R0 plus alpha 1 R plus alpha 2 squared, squared, that's cubed, and so on. So there are temperature coefficients associated with resistance. So if you leave your antenna up in the sunshine, and like we had a few weeks ago when you've got 40 and 50 degrees centigrade on your bit of wire, is it the same resistance as when you bought it from Dick Smith's or wherever, and you coiled it all up and you had it in your workshop sitting at 15 degrees centigrade? No, it won't be the same. So the next problem we have to concern ourselves with is, here we have a piece of wire, and we've got our current going along here. What determines the current carrying capacity of that wire? Sorry? We'll come to that. Let's just talk about the DC effects. DC effects first. Okay, so we're talking about the cross-sectional area and the material and the length. All right? So that's just talking about DC. So it doesn't matter if it's all coiled up and forms an inductance, or if there is capacitance between the turns in your coiling. It doesn't matter. But if we then start thinking about putting RF down this line, then we've got another kind of problem. We've also got a dielectric coefficient problem, and I'll come to that shortly too. So, I'm just talking here about a very simple form of antenna coupler. It's a pi coupler. All right, so we've got a variable capacitor, variable inductor, and another variable capacitor. So that's basically what you'll find inside most antenna coupling units. The problem is, God only gave us 2 hands. And to operate this bloody thing, we need 3. So there is a way around that. It's like this. Let's rearrange that device. All right. Now, all I've done is very slightly rearrange the circuit. I haven't changed anything. It's still exactly the same circuit, isn't it? Okay? But what we've now got here is an AC voltage divider. All right, say we decided that our antenna was going to be an off-center fed with an incoming impedance of, say, 200 ohms. And we've followed the American military and we've made this 50 ohms. All right. And so we put our capacitor here at around about 100 picofarad. Now, to get to this impedance here, what capacitance do we require here? Sorry?
Maybe 4 times size again.
4 times the capacitance will have 1/4. So it's 1 over 2 pi fc. Yes. Yes, okay. So we should aim for this one here being 25 picofarad, approximately. All right? Now, the capacitance is in series across this inductor. It's going to be about 33 picofarad. And if you put that across this inductor and you're going to operate at, say, 14 megahertz, the inductor needs to be, or say, we'll just put here 14 megahertz. This needs to be about 3.7 microhenries. So there's no magic, there's nothing unusual about this, it's just simple circuit theory. All I've done is slightly rearrange the circuit up there. And this is what we've got. It's a pi coupler. It's the kind of thing that if you ever played with valve radios, you've had a power supply, 8 microfarad capacitor, 10 Henry choke, 16 microfarad capacitor, and what's the frequency of resonance of that? It's about 25 hertz, so you don't get 50 hertz or 100 hertz coming through. Very effective pi filter. Okay. All right, I've done some calculations here from 1 watt up to, where have I gone? Kilowatt. And I've calculated the likely voltage across the input capacitor, this fella here. You can see the range there, 7 volts through to 224. So even if you're running a kilowatt, and you don't tell the radio inspector that you're running a kilowatt, and you don't let your neighbours discover that you're running a kilowatt, the voltage between the plates of that input capacitor is going to be about 224 volts. And because of the voltage breakdown coefficient, you could use an ordinary broadcast tuning capacitor at that point. But say we go to feed a 200 ohm antenna, I will come to that shortly, but that's the voltage at 50 ohms, and the voltage out of the whole device, somewhere between 2 volts and 2000 volts. So now the output capacitor, this fella, you really have to think about. You do have to have a bit more spacing. And particularly if you're going to use this antenna coupling unit for multiple frequencies. You also have to think about the kind of cable that you're using inside your... Now, in the inductor, I've assumed we're going to use some very good quality wire, and I've assumed that it's low resistance, good quality wire, and that you've designed the circuit in such a way that you achieve a quality factor of about 10. And so the current in your inductor runs from 0.3 of an amp up to 141 amps if you're running 1 kilowatt, depending on the downstream impedance that you're transmitting into. So you can't just go and buy an MFJ little box and it says, oh, you can tune up to a kilowatt on this, no problem at all. Maybe. Okay. So we're going to do a little bit of matching up now. So we've got an antenna, a transmitter output of 50 ohms, and we've set the antenna height at 1 lambda. It's going to be difficult if you're operating on 160 metres. Most councils won't allow you to have a 160 metre tower. You'll have to have a broadcasting licence. You'll have to be 2UE or 2GB or 2CF or whoever it is who has the 150 metre tower. Yes, yes, that's right, the navigation lights, that's right, yes. And say we want to match 50 ohms from our antenna coupling unit to between 5 and 100 ohms resistive all right? And we're going to go to a half wavelength antenna, a dipole, and it's going to be resonant at half a wavelength above ground. Now, we're going to have problems with that. As you remember back from the previous slides there, that the impedances jump all around the place. Okay, breakdown voltage of air, about 3 kV per millimetre. And this is what Kettering relied on in designing the first sparking system in petrol ignition motor vehicles. And they set the gap at about 1 millimetre, and because the engines are running about 3 to 4 to 1 compression ratio, they fit in 12 kV. And so they got a spark. But with our modern day engines, running sort of 8 and 9 to 1, then you need to actually either close the gap or have a much more powerful spark coil. And so some of the stuff that ETI turned out a long time ago, of instead of putting 12 volts across the coil, they put 400 volts across the coil, and then you're getting hundreds of kV going to your spark plugs. And your radio says, piss off, you're not allowed to talk today because I'm running the engine. Now, even in these capacitors here, if you've had problems like I've had recently where my workshop got completely flooded, I've got to go and open up things to see where the capacitor plates have started to corrode because the humidity's been up around 100%. Now, you can get around that. You have to go and talk with your bank manager, and you have to get capacitors with gold-plated plates in them so they don't get corroded. You might be lucky and pick up some military stuff which is silver-plated. The problem with that is we all love motor cars running up and down, and they're producing sulfurous oxides and nitrous oxides which add black stuff on your silver plates. Now, the sulfur oxide's okay, and the silver oxide's okay, but nitrous oxide's not so good. So that's why I'd suggest for the load capacitor that you go for much bigger than you actually require for voltage breakdown, that you could allow for corrosion. Okay, all right. So, we've already talked about the DC current carrying capacity of wire, depending on the cross-sectional area, the length, the covering, ambient temperature, all those kinds of things. And what you come up with if you assume that the wire can handle 5,000 amps per square inch is about 7.6 amps per square millimetre. Now, that's a sort of value that's used in design of transformers in Australia. You buy European transformers, you buy equipment that comes in and it says the label's 220 volts, and you're running it at 230 volts, so it's going to have more current flowing through it, and you'll find that it wasn't the engineer who designed the transformer, it was the accountant. And consequently, the wire will be thinner, and so it won't be running at 7.6 amps per millimetre, it'll be running at 10 or 12, and the tranny will get bloody hot. And worse than that, if you use an American transformer which is designed for 60 hertz, it will get hot as well, because you're running off the normal hysteresis curve and you're heating the transformer rather than transforming. Okay, now here's another little problem. The wiring in your house, hidden in behind the walls, is designed to carry 30 amps. 2.5 millimetre squared copper cross-section, okay? There's the construction of the wire, and when you do the calculations, you get 12 amps per millimetre squared. So what is Australian Standard 3000 assuming about our use of the mains? They're assuming that we don't have things plugged in all the time. But of course, with this weather out here, and we've all turned on our 2.5 kilowatt air conditioners, which are all drawing 10 amps, and you've got several of them in the house, so they're all giving the 30 amp circuit a bit of a walloping, and it's on all day and all night. What's happening to the wiring in the wall? Does your insurance cover your house being burnt down because the cable melts? Probably not. So you might want to run a different wire to your air conditioner. And where would you run? Under the house or in the roof space? Under the house? Why? I'm sorry?
If all the slabs been hard under the house.
Yeah, if you're built straight on a slab, yes, yes,
But
yeah.
if you've got floorboards under the house, it's just good.
Yes, put underneath. And why? Cooler, that's right, lower temperature. So the current carrying capacity of the wire is higher because of the lower temperature. However, if we're operating SSB or FSK, so one of those interrupted types of transmitters, then we can probably go up a bit because the wire will radiate and then it'll cool down. But if you're a leather-tongued award operator, in other words, you get on the microphone and you go on and on and on for half an hour at a time and you don't stop talking and you keep on filling all of your neighbours with all the rubbish that you've been thinking about for the last 10 years, the wiring is going to overheat, isn't it? When I was with Illawarra Amateur Radio Society, we actually had a leather tongue award. Yeah. For somebody who couldn't lift their finger off the push-to-talk button. It's still in existence, I believe. As you very rightly pointed out, RF is carried in the skin. Now, why is that? It's because the very high-speed waves inside the cable push the electrons out to the edge. Very simple. Now, if you just have, say, one skin depth, if you allow that your current carrying area is equivalent to one skin depth on the outside, then on the outside you'll be at plus J0, but on the inside you will have a phase shift of 1 radian. So your cables are no longer DC. They are actually starting to become inductive and capacitive, even straight copper cables. If you want to run a bit further, you might run to 4 skin depths and then you've got 4 radians of shift. I would suggest it might be better to go for 3 skin depths because you then get 3 radians and you're back to 360 degrees. But look at the difference in skin depth for a couple of different frequencies, 1 meg and 14 meg. And why is the current at 0.37? It's 1 over E, the natural base of logs, the Napier logs, developed just a little bit after Newton. Okay. So when we're designing our antenna coupling unit and the wiring going to the antenna coupling unit and the wiring afterwards out to your antenna, we need to consider frequency, current, and current density. So this might look like a very long calculator, but in fact it's as simple as this. So all I've done is calculated this area here. So I've taken the outside area of the conductor and subtracted the tubing on the inside. That doesn't carry much. And so I come up with approximately 1.75 radius divided by the square root of the frequency in megahertz. All happy? Any questions at this point? Bit different from what? Yes, go.
Would you recommend going from stranded cable or solid core?
Depends on the frequency. If you're wanting to operate down at top band, 160 metres, or even down to 500 kilohertz, then by all means use Litzendraht or any of the other stranded cables, because the skin depth will be greater than the diameter of the cable. But as the frequency gets up, then the skin depth becomes less and less. Yes?
Just an interesting thing. Most people would think, as I did, that skin depth had no effect at 50 hertz. If you go and have a look at major substation installations, it's all flat bar.
Yes.
And it's for exactly that reason.
Yes, that's right. Because at 50 hertz, the skin depth is 9.6 millimetres. So if you're carrying 4,000 amps, you're going to have a piece of cable this thick, and 9.6 millimetres is going to be this much.
In some of our stations, it's big hexagonal plate
There's another reason for that. They want very low inductance connectors in case of lightning strikes. And you can get low inductance by having very thin, wide straps. And so you have a different kind of conductor for lightning compared with RF. And if you've got your catenaries are running all the way up and down the country at 1500 volts DC until there's a lightning strike, and lightning strikes are, sort of 250,000 amps, 20,000 volts by the time it gets to the wire. It's going to do some cooking. Okay, let's see if we can move on. Is that system going to work? If I got to point it accurately? Right, okay, all right, okay. So let's consider 10 gauge at 28 megs. You can read the rest of that. So basically what I'm talking about there is the wire that you're going to use on the roller inductor. Bear in mind that if you have a roller inductor there and you're getting up to the higher frequency end of its operation, you're going to be just using 1 or 2 turns of that inductor, and the rest of the roller inductor is going to act like an auto transformer. And so instead of having 200 or 300 volts across the inductor, you might have up to 100 kV, and it's likely to flash over. And so you're operating away, then you talk and you hear this funny flashing sounds inside your antenna coupling unit. What have I done? We're going to use coaxial cable between our, say, antenna coupling unit, going up to our SWR sensor at the antenna. And these are 3 common coaxial cables that we're likely to use. RG213, RG58, and maybe if you're really working at UHF, RG174. That's the very small diameter stuff. Now, people talk about the dielectric constant. This says there's no such thing as constant. It varies with the frequency. Now, I haven't put up here LDF 450. It really starts up about here. And if you go to Gore Hill and you look at the transmission line systems they use there for television, they have 3-inch hollow copper tubing filled with nitrogen, so there's no oxidation going on inside the transmission line. And so they're going to be up around here. So if someone says to you, what's the dielectric coefficient? Isn't it a constant? Now you know it's not. And this is published data, published by Belden. So they know about it. But do the people who sell you the cable know this? Not so sure. Okay, all right. So now we're getting more and more into the design. Okay, so I've done some moderately detailed calculations here. If you're wanting to design your own antenna coupling unit, it's not that difficult. And I don't expect you to remember all this stuff. You can take photographs of it if you want. But there's a backup paper that I've produced for this presentation which goes into all the detail of the maths. And so you can just read it off and you can put in your own numbers. Now, I was going to bring along a little antenna coupling unit that I had built based on my design and that I had tested for its SWR on various frequencies, but I ran out of room. So unfortunately, I can't show you the device. But what I've got here is the calculations that I did for it. So it goes down to 1.5 megahertz. So I can't use it on the 500 kilohertz, the beacon bands, but I can use it on top band. And it's also good enough for 6 meters. but I can't use it for 2 metres or 70 centimetres or 23 centimetres. And there's the ratios which tell you something about the kinds of antennas that I could possibly use. So whether I'm going to use a multi-element Yagi-Uda, or whether I'm going to use a 200 ohm off-centre fed, or whether I'm going to use a dipole out in outer space. Come on, wakey, wakey. Oh, at last, all right. Here are some of the design considerations. Are we going? Okay, all right. So this is power out along the top. Impedance of your antenna here. And these are the voltages that you need to be concerned about inside your antenna coupling unit. So if you're going to run 10 kilowatts and you're going to use 600 ohm ladder line up to your antenna, your output capacitor is going to have to withstand 2.5 kV. And I happen to have one at home. So if you're wanting to run your Collins C310, just quietly let me know via email and I can send you the capacitor. Don't tell the inspector. Okay, so now you're starting to see that there are different kinds of voltages involved at different power and different frequencies. Now let's have a look at the current. All right, so here's some different kinds of current flow in the components at different antenna impedances and different output power of your transmitter. So if you're using a very simple Yagi antenna, 12 ohms, 28 amps. That's a sizable chunk of metal. Especially if your antenna element, you're going to use it for, say, 3 delta, 3 skin depths. You're going to be talking about tubing that's sort of this diameter. Come on, wakey, wakey. There we go. Right. So maximum current and power ratings. So if you bought something down below here and it was one of these little MFJ antenna coupling units, and you've got a 50 ohm transceiver and you feed it with a 50 ohm, or feed it into a 50 ohm transmission line into a 50 ohm antenna, there's your maximums. At 160 metres, 3 kilowatts, out to 10 metres, much less. So when you buy an antenna coupling unit, it isn't going to be universal for all frequencies and all powers and all impedances of antennas. So these are the things that you need to think about. And I won't over talk it, I'll let you read the stuff. Quanta Costa? Anyone else want to take photographs? No? Okay. All right. I think that's just about it. I've got a feeling that the next one is the references. Yep. Okay. That's some of the references that I used. In the actual paper that you can get a copy of, there are many more references. So I've actually gone into the soil chemistry and all sorts of stuff.